Okay, all right now. So what we would do today is this. We know sine, cosine, tangent, and we are going to meet the siblings of sine, cosine, tangent. They have siblings, okay? But I don't like the siblings. I like the originals, sine, cosine, tangent. But before we do that, the reason why I asked you to get a piece of paper to draw these 4 pairs of axes is because I would like to introduce different frames of reference so that you can tell angles at in different quadrants a lot easier. So let's start with this one. Okay. Now, we all know this is on the right-hand side of the x-axis. This is 0. Okay. So you can go ahead and put down 0. And we also know that at the top part of the y-axis, that's what angle in radians? That is pi over 2, right? Now, but the frame of reference I want you to have is that I want you to see how to express the angles if all the denominators are the same. So if I go ahead and put down the denominators of 2, how would you what would you put in the numerator? Over here. You put down 2 pi, right? Because 2 pi over 2 is the same thing as pi itself. So this is pi over 2, this is 2 pi over 2, and this will be 3 pi over 2. And back to the original location right here, this will be 4 pi over 2, which is 2 pi. Okay, so it's just a different way of seeing the same thing. And I would promise you this is going to be a lot easier for you to tell the angles in different quadrants a lot faster and easier. All right, now let's go to the one onto the right. So we'll start with 0 again. We'll start with 0. At the top, we are going to put down pi over, I'm sorry, my bad. I mean, not pi. I would like to start with the denominator of 6. Okay, so for all the other 3, or I mean the remaining 4, the denominators would be 6. So now, what should we put in the numerator? 3 pi, right? 3 pi over 6, which is the same thing as pi over 6, pi over 2, sorry, pi over 2. On the left, at 180 degrees, we will put down 6 pi over 6, right? Down under, we have 9 pi over 6. And back to the 2 pi location, 12 pi over 6. Right now. So if you have these all written out, I hope it makes sense. First, does it make sense? Yes? And the second thing I want to emphasize here, well, I mean, not emphasize, I want you to now use it. Let me show you the utility of this frame of reference. If I ask you, guys, where is 7 pi over 6? Which quadrant? 3. Because 6 pi over 6 is right here. So 7 pi over 6 must be the next quadrant. Okay. So 7 pi over 6 must be right here. What about 11 pi over 6? What about 5 pi over 6? What about 13 pi over 6? Back to 1. Now, can you see how you bypass the thinking of degrees, and you can still tell the quadrants a lot very quickly? Now, when I was a kid learning these trig functions, I was not very smart, or I can say I was stupid. I would change all the radian angles to degrees and tell the quadrants that way. I try to fight the battle of I don't like radians, I like degrees. Change everything to degrees. Time and time again, I did it. It wasted me a lot of time. And when I went to calculus, I realized that there is really no point to be stubborn for this matter. It's actually much better for you to get used to radians, but still, sometimes if you look at 5 pi over 6, 7 pi over 6, it's not so very intuitive. So over the years, I was like, how can I make this more intuitive? And I realized that the way you can make the conclusion process a lot easier and more efficient is to have a separate frame of reference. Now let's keep going. What if I would like you to use I will put the 4 into the denominators. Okay, put 4 into the denominators. What should you put at the 90-degree location? 2 pi over 4, right? And then you have 4 pi over 4. And then you have 6 pi over 4. And then, of course, you have 8 pi over 4. So if I ask you, hey guys, where is 5 pi over 4? Quadrant 3. What about 3 pi over 4? 2. Okay, you know how to split the whole circle into different parts, and you know how to use the denominator to assess the location approximately. And for the last one, it could look a little bit weird. We would like to use a denominator of 3. So at the 90-degree location, that would be a 1.5. Okay, it's just for reference. Okay, of course, we know we shouldn't use a decimal in the numerator, but just for reference. 3 pi over 3, 4.5 pi over 3. So if I asked you, where is 4 pi over 3? Quadrant 3. Where it's 2 pi over 3? Quadrant 2. Where it's 5 pi over 3? Okay. Oh, I forgot to write down 6 pi over 3. Yeah, so 6 pi over 3 right here. So 5 pi over 3, it's apparently in between 4.5 pi over 3 and 6 pi over 3. So I hope this way of thinking would reduce your mental pressure of recalling these values. And also, when you look at your unit circle, make sure you also know how to label the angles properly. Okay, good. Now, just a reminder, you need to start working on remembering all the values, all the blanks, all the coordinates on the unit circle. Next Monday, you will be given a unit circle with all those blanks, and you have 10 minutes to finish them. Okay. Now, as I said yesterday, there are patterns. So make use of the patterns to retain the values. Okay. This will be 3 pi over 2. Okay, all right. So now we have cosine, sine, tangent. Okay. Let's write down the ratio of these 3 trig functions. So cosine theta is adjacent over hypotenuse. Okay, you can finish the remaining. Sine theta is opposite over hypotenuse. And tangent theta, it's opposite over adjacent. Oh, by the way, did you learn this in geometry? That tangent theta could also be expressed as sine theta over cosine theta? Okay. We'll see them more. We will play with all these trig functions a lot more, and you will love them. And please do love them. If you don't love them, you'll get hurt. So, not by me, but by these functions. Now, so these are the functions you have seen before. And now we have something to the right-hand side of it. We have secant, cosecant, and cotangent. So this is what I call them, the siblings of sine, cosine, tangent. And the reason we arrange them this way, left and right, is because we want you to pair them. We want you to pair them up. So secant theta, it's actually known as 1 over cosine theta. Okay, and what do we call this kind of relationship between secant theta and cosine theta? How many of you say inverse? Any other suggestions? Now, whenever I ask this question, like what's the relationship between cosine and secant? Now, most of the time I heard inverse. Sometimes I hear people saying opposite. They're both wrong. First, opposite is wrong because there are a lot of opposites. Like there are opposite, like positive and negative, they're kind of opposite. And there's so many opposites, and the word opposites just doesn't mean much. And inverse is not like this. Inverse is like what? Log and exponent, square and square root, right? This is not inverse. This is what we call, starting with the R, reciprocal. Now, and I'm writing this down because I want to make sure that you know how to use the correct word to describe it. If you cannot even say the right word to describe the relationship, well, that means you don't know what's going on in your head. So please write this down, reciprocal, okay? Make sure you know it's the reciprocal. So secant theta is the reciprocal of cosine theta. And because it's the reciprocal, what can you say about the ratio? It becomes hypotenuse over adjacent. Okay, the same goes to cosecant theta. Cosecant theta, it's 1 over sine theta, which is equal to hypotenuse over opposite. Okay. Now, here's another question, though. So we need to memorize them, sadly. So how can you make sure that you don't memorize the wrong thing? I mean, for me, from personally speaking, I just find it hard to relate secant theta, the name itself, secant and cosine. It's just hard. There's no obvious clue to relate them. So now this is my way of relating them together. Look at the first letter. They must be different. Okay, look at sine and secant. Oh, the sine and cosecant. They are also different. So if you ever mismatch them, then they will be the same. And then you would know that, hey, you did something wrong. Now that's my way. Okay, that's my way. You can develop your way. I don't really care which way you use. All I care is you don't do it wrong. Okay, so it worked for me pretty well for the past 20 something years. So you may use it as a reference. And tangent and cotangent, I think that's easy. You don't really need much to remember it. So cotangent theta, it's simply 1 over tangent theta, which is equal to, you can talk about cosine over sine. Okay, cosine theta over sine theta, or you can also equal to adjacent over opposite. Okay, so which one do we use? Well, depending on what are we talking about. So that's also part of the decision-making process we need later on in this course, but not so soon. Okay, not so soon. Now, let's look at your, well, any question first for the siblings of sine, cosine, and tangent? Okay. Now, one more thing, in case you don't have any question, one more thing is this. I personally, as I said at the beginning, I do not like the siblings. I do not like the secant, cosecant, and cotangent. So whenever I see them, I would immediately think about the sine, cosine, tangent. If I see the secant, I would think about this as 1 over cosine. Okay, I will show you, but just trying to share with you that my personal feelings about these trig functions. Right now, if you look at your unit circle, okay, if you focus on quadrant 1, so go ahead, look at quadrant 1 of a unit circle. Can you see the coordinate value of 1/2? Can you see it? Okay, so what is the angle that gives you the x value, the x value of 1/2? 60 degrees, right? So when we say 60 degrees, the x value is what? Sine or cosine? It's cosine, right? So if x is equal to 1/2, we can say cosine 60 is equal to 1/2. Now in the first quadrant, still in the first quadrant, can you see another coordinate of 1/2? Where is it? What angle? 30 degrees, right? And what's the coordinate? Is it the x or the y? So so that means we have sine of 30 degrees. It's equal to 1/2. Is it a coincidence that they are the same? Like 1/2 and 1/2? Is it a coincidence? Now, let me also direct your attention to 45 degrees. What's the x value for x coordinate for 45 degrees? Root 2 over 2, right? So x value, it's cosine. So cosine 45 degrees is root 2 over 2. And what about the y value? It's also root 2 over 2. Can you see something special? They are complementary. Can you see how they add up to 90 degrees? And somehow they have same values. You switch the trig function and you get the complement angle, and somehow the value will be the same. And this is exactly the meaning of cofunctions. Is that the sine of an angle, it's equal to the cosine of its complement angle. And what's the meaning of complementary angles? Add up to 90 degrees, right? Add up to 90 degrees or pi over 2. So with that said, secant and what functions are cofunctions? Secant and cosecant. They're cofunctions. Tangent and cotangent. Okay. So one thing you can write down below is this. So the way we express this idea, and I think you might need to know this for SAT, is that sine theta is equal to cosine of 90 degrees minus theta. Sine theta, it's equal to 90 degrees, cosine of 90 degrees minus theta. Now, at the very beginning, you may find this kind of expression very strange. And that's why I asked you to come up with these values first, because now you can say, oh yeah, sine 30 degrees, 1/2. It's also equal to cosine of 90 minus 30, which is 60 degrees. So they are actually the same thing. Sine 30, it's equal to cosine of 60. Sine 45, it's equal to cosine of 45. Okay? So, so cosine theta, it's equal to sine of 90 minus theta. Okay, so so we can also say this. All right. All right, now let's go ahead and focus on the bottom. Now we can go back to the 6 functions. So the example down here, it says we have a point. Remember we did this. Remember we did this 2 days ago. We put a dot on the coordinate plane. So 3, -4. Where should we put the dot? Which quadrant should we put a dot? Quadrant 4. Okay, so the dot, it's going to be somewhere right here. Okay, so this is 3, this is -4. And you can go ahead and draw a little triangle. Okay, and this is what we call a reference triangle. Now, the key thing about reference triangle is that's the baseline must be on the x-axis. And we will go ahead and write down our. We'll go ahead and write down our 6 trig functions. So we have sine theta, cosine theta, tangent theta. And then right next to it, we will put down cosecant theta, secant theta, and cotangent. Oops, cotangent theta. So I would like to pair them up like this. Why? They're reciprocals, right? So if you did this, you just flip it. Okay. Are we good? So now I just want to make sure that that you know something. Remember last 2 days ago, I also drew you this one, ASTC. Now we're going to use this for quite a few times, and the more you do, the better it should stay in your mind, stay in your memory. Okay, what's the meaning of this diagram? The what? Whichever. Yeah, the sign, the which function is positive. So all, and this is for sine. And if sine is positive, what else is also positive? Cosecant is also positive. Tangent and cotangent, cosine and secant, right? Right. So now, if we know the angle, it's located in quadrant 4. So what must be positive? Cosine and secant must be positive. So therefore, we can actually put down the minus onto the other 4 functions. And we also know that where this negative comes from, the negative comes from the -4. Okay. But if you place the minus ahead of time, then one thing I can guarantee you is that you will never forget about the signs. So the length is 3. This is 4. What's the hypotenuse? It's a 5. So now you just need to get all the ratios in place. So sine theta is 4/5. Opposite over hypotenuse. And cosecant is just the reciprocal. Cosine theta is 3/5. So secant theta it's 5/3. Tangent theta is 4/3 negative, because the 4 is negative. Tangent theta, cotangent theta would be 3/4 negative. Easy, very easy. Okay. All right, now let's take a look at part B. Part B, it's a little bit challenging. It's a bit challenging. So for part B, which quadrant should I put the dot in? Quadrant 2, because it's -4, and then √5 is somewhere right there. So so if you draw your triangle, it will be something like this. Okay, that's a point. That's a theta. Okay, so you have the length of two sides. That is √5. This is 4 with a negative. What is the hypotenuse? What is the hypotenuse for this? Square root of 21. Very good. Okay. Now, I hope by seeing the square root, you may sense something is coming. What is this something? Yeah, you may need to rationalize it. It's not something that's pleasant, but yeah, it happens. Okay, so it's in quadrant 2. So can you tell which one is positive, which function is positive, which one is negative? Which one? Sine and cosecant and positive. So the remaining 4 must be negative. And we'll go ahead and fill in the ratios. And if we need to rationalize, we will rationalize. Okay. So sine theta is opposite over hypotenuse. So that means √5 over √21. √5 over √21. Okay, and because we need to rationalize it, so we need to multiply √21 over √21. So the denominator would be 21, and the numerator would be square root of 105. Yes. Why is it 21? Because the hypotenuse is 21. How did you find that? All right. The hypotenuse, we use Pythagorean theorem. So so a squared plus b squared is equal to c squared. So so we just put in here √5 squared plus 4 squared. So 5 plus 16 is c squared. C squared is 21. So c is c is √21. Okay. All right, now what about the cosecant? Should we use the reciprocal of root 5 over 21, or should we use the reciprocal of 105, square root of 105 over 21? Which one is better, the left or the right? The right one. Which one should we reciprocate? The left one. Why is it the left one then? Now you have to do rationalization anyways. But if you use the square root of 105 over 21 and you reciprocate that number, you will end up with a gigantic number. We never like gigantic number. So we just do square root of 21 over square root of 5. And then we multiply by root 5 over root 5 to rationalize it. So the numerator will be root 105, but the denominator is just 5. Okay. So I think this is the worst one. Other ones are actually better. So cosine theta, it's actually better. What's cosine theta? Oh, actually, not really, but not as bad. 4 over root 21, adjacent over hypotenuse. Still need to rationalize it, but it's a lot easier. So 4 root 21 over 21. Don't forget the negative. The negative is still there. Okay, the negative is still there. Secant theta, we will have, ooh, that's nice. Root 21 over 4. No need to rationalize. Sweet. Tangent theta, opposite over adjacent. Very nice. With 5 over 4, with the negative up front. And cotangent will be 4 over root 5. So just an easy rationalization. So equal to negative of 4 root 5 over 5. Okay, so what do you feel? Can you handle this? Okay, so it's just breaking down a triangle, knowing which quadrants, knowing what signs they are, and that's really what we do here. Now, let's go to the bottom half of the page first for the back page. And since we were just talking about the quadrants and the signs, let's make some good use of it. So this table, which is not something that is for you to memorize because that's not a user-friendly table at all. But we just want to know if you know how to use this picture. So now let's focus on the positive. As always, focus on the positive. So quadrant 1. In quadrant 1, what functions are positive? All of them. So put down positive for all of them. Quadrant 2. Only. Sin n, cosecant. Okay. For me, I will look at the first letter, making sure that they're the same, that they're different. Quadrant 3. Tangent and cotangent. Quadrant 4. Cosine and secant. All right. So everything else will be minus. Now this is how I do my minus. Not that I care about this table, but I just don't want to. I don't want to hurt my eyes. If I'm just putting like minus and plus without the circle, it's going to hurt my eyes pretty badly. Now, based on this table or based on this diagram, ASTC diagram, can you decode or solve the puzzle right here? It's that if secant theta and cotangent theta have opposite signs, meaning 1 plus, 1 minus, in which quadrants can theta lie? Quadrant. Can it be quadrant 1? Because they are all positive, right? Can it be quadrant 2? It will be? Nope, because they will be both negative. So now, so let me tell you how I would analyze this. Again, I do not have a good feeling with secant and cotangent. So whenever I see secant theta, I would immediately think about this as 1 over cosine theta. Whenever I see cotangent, I would immediately think about 1 over tangent theta. So that I can make use of this diagram a lot more effectively and accurately. So I'm thinking about, they must have opposite signs. Not quadrant 1, not quadrant 2. It must be quadrant 3 and quadrant 4, because in quadrant 3, cosine is negative. And tangent is positive. In quadrant 4, cosine is positive, tangent is negative. So that's kind of like the logic puzzle, okay, that you will need. All right, now we can move back to the top part because it's really the same thing. The theta is in quadrant 3, but instead of giving you a dot, now we're giving you a function. So we're saying that, yes, we're saying that, hey, secant theta, it's a negative 13 over 5. Why is secant negative? Why is secant negative? Because that it's a 1 over cosine, it's in quadrant 3. In quadrant 3, only tangent's positive, so of course secant is negative. And what does the 13 over 5 ratio mean? What does it mean? Hypotenuse over adjacent. So that means you can use this piece of information to draw a little triangle. You say, oh yeah, I can draw a little triangle right here. And I can tell the sides, this is 13, this is 5, and that's the reason why we have a negative 5. Quadrant 3, right? This is a negative x-axis. And what's the vertical side right here? It must be 12. Okay, so yeah, if you're taking the SAT, you must know the 3, 4, 5 triangle. You must know the 5, 12, and 13 triangle. The Pythagorean triplets, or triples, whatever they call it. Now, can you write out the 6 functions? Okay. Now, I have another suggestion for you. There's another way I can do the same thing. I can obtain the same answer, but I can draw another more user-friendly diagram. So this is just an option for you. Okay, this is just an option for you. You can choose whichever one you prefer. All I care is that you get the correct answer. So after I know it's in quadrant 3, that means I know my positive sign and negative signs. I know that only tangent is positive, everything else is negative. And since I took care of the sign, I can focus on the triangle. I can just draw a generic triangle. Actually, I want to draw it this way to be more relevant. And I want to draw a triangle like this. And this is my theta. Because hypotenuse over adjacent, hypotenuse over adjacent. And I'm going to use this triangle to take care of my ratios. I'll be like, oh, sine theta, 12 over 13. Cosecant theta, 13 over 12. Okay, so it took away my pressure of drawing this triangle correctly on the axes. I need to make sure which quadrant it is. I need to make sure the signs are proper, they are accurate. And then I just use the length of the triangle to get all the ratios. So cosine theta is 5 over 13. Secant theta is 13 over 5. Tangent theta, it's positive 12 over 5. And cotangent theta is 5 over 12. Okay, so again, you can draw the triangle at the axes. Okay, or you can draw the triangle separately. Just make sure that you took care of the signs, whether it's positive or negative. Then you'll all be good. Now, when you get your worksheet, I would like you to go to the back page, second page. Go to the second page. And now we can put all the things together. You look at this. Which quadrant is this angle? Quadrant? 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 (16 pi over 16 pi), it's 1 pi, right? Well, this is greater than 16. Now, of course, it's not the same as what we did earlier, but the logic is the logic that matters. Okay, so sine of an angle in quadrant 3 must be positive or negative? Negative. Okay. 2 pi over 3. Quadrant. Okay, look at the paper. Look at the paper that we had earlier. If you need some help, 2 pi over 3, it's in quadrant 2. Okay. So cosine of an angle in quadrant 2 must be negative. All right. Cosine of pi over 2. Now, pi over 2, it's not a quadrant. It's actually on the axis. It's on the y-axis, right? And on the y-axis, cosine of pi over 2, cosine is the x value, right? So look at the unit circle. What's the x value when the angle is pi over 2? Pi over 2? 90 degrees. Yeah, well, I mean, this is equivalent to 90 degrees. The cosine of pi over 2 is 0. Okay. The one to the right, ooh, this is a big angle. Now, what happened when you see this kind of big angle, 7 pi over 2? Now, that means it has gone through at least one cycle, one revolution. So what you can do, go ahead, subtract 2 pi or 4 pi over 2. Because after you finish one cycle, everything just resets. So just go ahead and subtract 4 pi over 2 because we subtract one revolution from this big angle. So 3 pi over 2, it's on also x-axis, but down there. And it's a sine 3 pi over 2. That means it's the y value. What's the y value over there? Y value. -1. Okay. So when you see big angles, that's what you do. All right. Now, remember, go home, get started with your unit circle practice. Okay.